Not all chemistry happens in a beaker. Some happens in the sky above our heads, in the atmospheres of planets across our solar system, and even in the space between the stars. In these environments without catalysts or heat to overcome chemical activation barriers, only the most facile reactions are able to occur. Ultraviolet light from our sun kickstarts this chemistry in our solar system by breaking molecular bonds, seeding free radicals in the atmosphere. These highly reactive molecules are responsible for many reactions that occur in our atmosphere, which can lead to molecular growth, which generates harmful particulate matter, or the removal of greenhouse gases and pollutants.
Hello, I'm Dr. Charles Markus, 2020 A.O. Beckman Postdoctoral Fellow. I've been working with Professor Michio Okamura at the California Institute of Technology and Dr. Stan Sander at the Jet Propulsion Laboratory to develop new techniques for investigating fundamental chemical processes which have profound impact on our climate, human health, and understanding of chemistry throughout the universe.
Instead of glove boxes or round-bottom flasks, my tools are vacuum chambers and lasers. I typically start reactions with a blast from a high-energy UV source, often an excimer laser, and with careful timing, I use infrared lasers to monitor the different products and reactants as they evolve in time.
Molecules reduce the amount of light that passes through them at specific colors or wavelengths in a process known as absorption, and this provides a unique signature for every molecule. Now, the strength of these signals depends on the distance that light travels through a sample, and techniques which maximize this interaction length can be incredibly sensitive.
This can be done with specialized mirrors designed to reflect the light back and forth a few dozen times. For example, at NASA's Jet Propulsion Laboratory, I have been measuring the evolution of OH and HO2 radicals simultaneously. If one of the lasers shifted just 1 picometer in wavelength, no absorption would be observed. This makes infrared spectroscopy extremely powerful for unambiguous detection and for monitoring multiple species at the same time. In order to investigate the critical radical terminating step, OH plus HO2, I have developed new methods for generating Hawkes radicals, which provides a cleaner measurement of the cross-reaction without interfering side or secondary chemistry. These results have helped confirm models of chemistry in the lower atmosphere, which is closely coupled to pollutants such as ozone or photochemical smog. Beyond multipass cells, even longer path lengths are possible by taking advantage of the principle of optical resonance. Two mirrors facing each other form an optical cavity. If the wavelength of incoming light fits an integer number of times between the two mirrors, each round trip will constructively interfere. As you can see here, as the distance between the two mirrors is increased by even a small amount, the transmission suddenly jumps when it crosses a resonance. This provides hundreds or even thousands of meters in optical path length within a small experimental setup, allowing for extremely weak absorption signals to suddenly become observable.
Now, monitoring one or two species is useful, but in many reactions it becomes necessary to track many different product branching paths at the same time. And this is where a relatively new laser technology known as optical frequency combs have generated a lot of excitement. Now, these are broadband sources composed of discrete narrow comb teeth spaced at a highly regular interval. And this provides the benefits of narrowband lasers with broadband coverage, acting like 100 or thousands of lasers in one. Another nice property is that this regular spacing can be matched to the resonances of an enhancement cavity, and many of the comb lines can be on resonance simultaneously.
In the apparatus I constructed at Caltech, the comb is generated with an interband cascade laser, or ICL. Fabricated at JPL's Microdevices laboratory, this technology promises to simplify and miniaturize frequency comb spectroscopy in the mid-infrared. Here you can see as the current is increased, the device changes from single-mode operation to transmitting a comb. The comb modes are slightly mismatched from the cavity resonances, such that each comb tooth transmits in sequence as the cavity length changes, providing a robust measurement of the comb spectrum. With each shot of the excimer, we get information about the absorbance at each comb tooth at different points in time. By scanning the delay between the UV laser and the comb measurement, we can fill in both time and frequency. Here, we can see the oxidation of methanol to generate formaldehyde, an extremely rapid process. The appearance of rotational fine structure from formaldehyde and hydrochloric acid allows for their concentrations to be tracked simultaneously with a time resolution of 100 microseconds. This robust and simple approach to direct frequency cone spectroscopy will open doors to new investigations of gas phase kinetics, important to our Earth and beyond.
It's been a real honor to even be a small part of Arnold Beckman's legacy. Dr. Beckman famously brought spectroscopy to chemistry laboratories with the spectrophotometer, making it part of the chemist's standard toolkit, even to this day. And I would like to thank the Beckman Foundation for all their support, which has opened up so many amazing opportunities for me in developing new technology with optical frequency combs and exploring the chemistry of exotic transient species. I'm excited to bring all that I've learned with me onto my next step, pursuing new frontiers at NASA's Jet Propulsion Laboratory.